Hello there and welcome to Theories Before Sleep. I'm so glad you're here. Maybe it's been a long day. Perhaps your mind is still racing with thoughts of deadlines and obligations. Or maybe you're simply curious about space-time, seeking something peaceful to carry you into sleep, a gentle voice to accompany you through the darkness. Tonight's journey is for you. You don't need to do anything but rest. Let your breath slow, your thoughts soften, and your body grow light. There's no effort required, no test waiting at the end. We're going to explore 100 theories about space-time, not in a rush, but slowly, gently. From the fabric of reality to the nature of temporal flow, each theory a quiet doorway into wonder. Some will feel familiar, others strange. All are presented to help you drift peacefully towards sleep, carried by curiosity into rest. If these explorations help you unwind, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The first theory is waiting, patient and quiet. Space and time are woven into a single fabric. Einstein showed us that space and time aren't separate things but unified into something called space-time. This insight emerged from trying to understand how light behaves, how motion affects measurement, how gravity shapes reality. Before Einstein, we imagined space as an empty stage where time marched forward independently, the same for everyone everywhere. But space-time is different. It bends and curves around massive objects, like a rubber sheet sagging beneath a heavy ball. Time flows differently depending on gravity and speed. A clock near a black hole ticks slower than one floating in empty space. An astronaut travelling near light speed ages less than someone standing still. Space and time are intertwined, inseparable, forming the fabric upon which everything unfolds. We move through this fabric constantly, travelling through time as surely as through space. The universe isn't happening in space-time but is space-time, geometry itself alive with motion and meaning. Space-time might have more than 4 dimensions. Our experience reveals 4 dimensions, 3 of space and 1 of time. But some theories suggest hidden dimensions exist, curled up so small we cannot perceive them. This idea emerged from attempts to unify physics, to explain why fundamental forces behave as they do. String theory, for instance, requires 10 or 11 dimensions for its mathematics to work. The extra dimensions might be compactified, rolled into tiny loops smaller than atoms, present everywhere but invisible. Like a garden hose viewed from far away appears one-dimensional, a line, but up close reveals a second dimension wrapped around its length. These hidden dimensions could influence particle physics, determining properties we observe. They might explain why gravity is weaker than other forces, leaking into dimensions we cannot access. Perhaps reality has more room than we imagine, vast spaces perpendicular to everything we know, forever beyond our sight, but shaping what we see. The block universe suggests all time exists simultaneously. In this view, past, present and future are equally real, existing together in a 4-dimensional block. Time doesn't flow, but simply is, stretched out like space. This theory emerges from relativity, which treats time as another dimension, no different fundamentally from spatial dimensions. If true, your birth and death exist simultaneously, along with every moment between. The sensation of moving through time would be illusion, consciousness experiencing sequential slices of an eternal structure. Yesterday still exists, tomorrow already does, all moments frozen in crystalline arrangement. Events don't happen, then cease to exist. They remain forever in their temporal locations. We experience flow because consciousness moves through the block, encountering moments in sequence, but the moments themselves are static, unchanging, eternal. It's a strange and beautiful idea, that nothing is truly lost, that every moment of joy remains real somewhere in the structure, that time is less like a river and more like a landscape we traverse. Space-time, curvature creates what we call gravity. Einstein's general relativity revealed gravity isn't a force but geometry. Massive objects curve space-time around them, and other objects follow the straightest possible paths through this curved geometry. This insight revolutionized physics, replacing Newton's mysterious action at distance with elegant geometric necessity. Imagine space-time as a trampoline. Place a bowling ball in the centre, and it creates a depression. Roll a marble nearby, and it spirals inward, not because the bowling ball pulls it, but because it follows the curved surface. Planets orbit stars not because invisible forces tug them, but because stars warp space-time and planets travel along the curves. Light bends near massive objects for the same reason, following curved geometry, even time curves, flowing slower in stronger gravitational fields. This curvature is gravity, geometry itself becoming dynamic, responsive, alive. Mass tells space-time how to curve, and curvature tells mass how to move, an eternal conversation between matter and geometry. Quantum mechanics and general relativity conflict at small scales. Our two best theories describe different realms beautifully but cannot be reconciled. Quantum mechanics governs atoms and particles, treating space-time as a fixed background. General relativity describes gravity and cosmos, treating space-time as dynamic geometry. Both work perfectly within their domains but contradict each other when applied together. At the Planck scale, unimaginably small, both theories should apply simultaneously. But their mathematics clash, producing infinities and nonsense. Quantum mechanics says particles exist in superposition, multiple states at once. But general relativity requires definite geometry. How can space-time be both curved and uncertain? This tension has driven decades of research, seeking theories that unite quantum and gravitational realms. String theory, loop quantum gravity, and other approaches attempt this unification. The answer might reveal space-time itself is emergent, not fundamental, arising from something deeper we haven't yet imagined. The mystery remains, patient and quiet, waiting at the boundary of the very small and the very massive. Time might not be fundamental, but emergent. Some physicists propose time isn't a basic feature of reality, but emerges from something more fundamental. This radical idea suggests the universe's deepest level is timeless, and temporal flow appears only at larger scales, like temperature emerging from molecular motion, even though individual molecules have no temperature. In this view, the fundamental laws might be time-symmetric, with no distinction between past and future. Time's arrow, its apparent flow from past to future, could emerge from entropy, from statistical properties of complex systems. The sensation of time passing might be an artifact of consciousness, a way our minds organize experience. Perhaps at reality's foundation, everything simply exists in eternal configuration, and time is the story we tell about relationships between states. This doesn't mean time is illusion, only that it's not fundamental, not woven into reality's deepest fabric. Like wetness emerges from water molecules, but no single molecule is wet, time might emerge from timeless components, real but not basic. Space-time foam suggests tiny quantum fluctuations everywhere. At the Planck scale, space-time might not be smooth but bubbling with quantum fluctuations. This concept, proposed by John Wheeler, envisions reality's fabric as foaming, seething with virtual particles and tiny wormholes appearing and disappearing constantly. Space and time themselves become uncertain, probabilistic, grainy rather than continuous. These fluctuations would be impossibly small, far below anything we can measure. But they might have consequences, affecting particle physics, potentially explaining certain anomalies, Space-time foam suggests reality at its smallest scales is wild, chaotic, nothing like the calm geometry we experience. Virtual black holes might flash into existence for infinitesimal moments. Topology itself might fluctuate, connections forming and dissolving faster than thought. Yet from this quantum chaos, smooth space-time emerges at larger scales, like ocean appearing calm from far away, though molecules dance frantically. The foam remains speculative, impossible to observe directly, but it captures something profound, that even space and time might be quantum, uncertain, strange at their foundations. Closed. Time-like curves could allow time travel. General relativity's equations permit solutions containing closed time-like curves, paths through space-time that loop back to their starting points in time. These mathematical possibilities suggest time travel might not violate physics, though whether nature actually allows it remains unknown. The equations permit it, but reality might forbid it through mechanisms we don't understand. Rotating black holes, certain wormhole configurations, and other exotic geometries could contain these curves. An object following such a path would travel into its own past, encountering itself at an earlier time. This creates paradoxes. What if you prevented your own departure? Physics has no clear answer. Perhaps consistency conditions prevent paradoxes, or perhaps timelines branch, or perhaps closed time-like curves exist mathematically but not physically. The possibility remains tantalizing and strange. A whisper in the equation suggesting time might be less linear than we assume, that future and past might connect in ways we cannot imagine, that causality itself might be more flexible than experience suggests. The holographic principle suggests space-time is a projection. This theory proposes that all information in a volume of space can be encoded on its boundary, like a hologram encoding three-dimensional images on two-dimensional surfaces. The idea emerged from studying black holes, which seem to store information on their event horizons rather than in their volumes. If true, our three-dimensional reality might be a projection from a two-dimensional surface, perhaps at the universe's edge. Everything we experience, every particle and force, could be encoded on this distant boundary. Space itself might be illusion, depth emerging from flat information. This doesn't mean reality is fake, only that its fundamental description might require fewer dimensions than we perceive. Like a hologram appears three-dimensional, but is encoded in two dimensions, space-time might be encoded on a lower dimensional surface. The mathematics works beautifully in certain contexts, suggesting deep connections between gravity, quantum mechanics, and information. The principle remains speculative but hints that space-time might not be what it seems, that reality's true nature might be stranger and more economical than our senses suggest. Space-time might end at singularities. At the centers of black holes, general relativity predicts singularities, points where curvature becomes infinite and space-time itself breaks down. These aren't just places where matter is compressed, but where the fabric of reality ends, where the equations produce infinity and cease to make sense. Singularities represent the limits of our understanding. Physics cannot describe what happens there because space-time, the stage on which physics occurs, no longer exists. Time might end, space might collapse to a point, all familiar concepts failing. Some physicists believe singularities indicate where general relativity breaks down, where quantum effects must dominate. Perhaps quantum gravity, when we understand it, will smooth singularities into something less extreme. Or perhaps they're real, genuine edges where reality terminates. We cannot know without a theory uniting quantum mechanics and gravity. Until then, singularities remain mysterious, places where our best descriptions fail, where space-time reaches its limits and we reach ours. As we move deeper into spacetime's mysteries, the questions become more layered, more strange. The next theories explore the nature of temporal flow, where physics meets philosophy in quiet wonder. The arrow of time might be statistical. Rather than fundamental, time appears to flow in one direction, from past to future, yet fundamental physics laws work equally well in both directions. This puzzle has troubled physicists for over a century. The arrow of time, our sense of temporal flow, might emerge from thermodynamics, from entropy's tendency to increase. In a low-entropy state, highly organized, there are few possible configurations. In a high-entropy state, disordered, there are many. The universe began in low entropy and evolves toward higher entropy, and this statistical tendency might create time's arrow. We remember the past because low-entropy states are rare and distinctive. We don't remember the future because high-entropy states are common and indistinguishable. Time's flow might be perspective, a consequence of living in a universe moving from order to disorder. At the fundamental level, time might be symmetric, directionless. But for beings like us, embedded in entropy's flow, time has an arrow, pointing always from the structured past toward the disordered future. Minkowski space-time unifies space and time mathematically. Hermann Minkowski, Einstein's former teacher, formulated a mathematical framework treating space and time as unified. In Minkowski space-time, events are points in four-dimensional geometry, and intervals between events combine spatial and temporal separations. This framework became the foundation for special relativity. The mathematics reveals that what one observer calls space, another might call time, depending on their relative motion. Space and time mix together under motion, trading places in precise mathematical ways. This unification isn't just philosophical but calculable, predictable, testable. Minkowski space-time has a geometry different from ordinary space, with a minus sign in its metric that distinguishes time-like from space-like directions. This geometry is flat, without curvature, but still profoundly different from Euclidean space. It represents the stage on which special relativity plays out, the arena where light speed is constant and simultaneity is relative. The framework is elegant, beautiful, revealing deep unity beneath apparent separation. Proper time measures duration. Along world lines, in relativity, each object has its own proper time, the duration it experiences along its path through space-time. This path, called a world line, traces the object's journey through four-dimensional geometry. Proper time is what a clock travelling with the object would measure, the subjective duration of its journey. Different world lines between the same events can have different proper times. An astronaut travelling at high speed ages less than someone remaining stationary, not because time is weird, but because their world lines through space-time have different lengths. Proper time is invariant, the same for all observers, even though coordinate time is relative. It's the closest thing to absolute duration in relativity, the time that matters for physical processes, for aging, for decay. Every particle, every person, every object carries its own proper time, its own measure of duration, independent of how others perceive it. We each travel through space-time at our own rate, experiencing our own flow, our own rhythm, connected to others through geometry but separate in our temporal experience. Causal structure determines what can influence. What space-time has a causal structure, a pattern determining which events can influence which others. This structure is fundamental, more important than coordinates or specific measurements. Events can influence other events only if light or slower signals can travel between them. The light cone is central to this structure. From any event, future light cone contains all events that could be influenced by it. Past light cone contains all events that could have influenced it. Outside the light cones lies elsewhere, events that cannot affect or be affected by the central event. This structure is absolute, unchanging under motion or perspective. It defines causality itself, ensuring effects follow causes, preventing paradoxes. No matter how observers move or how they measure, they agree on causal structure, on which events could influence which. This structure is space-time's skeleton, the framework ensuring consistency, preventing chaos. It's beautiful in its simplicity, profound in its implications, the foundation of everything that happens. Tidal forces arise from space-time curvature. Variations. Gravity isn't uniform but varies across space, and these variations create tidal forces. Near a black hole, for instance, the gravitational field is much stronger at your feet than your head, stretching you like taffy. This stretching isn't from gravity's strength but from its variation, from space-time curvature changing across distance. Tidal forces reveal curvature directly. In uniform gravity floating freely, you'd feel weightless, but in varying gravity you'd feel stretched or compressed. These forces are real, measurable, destructive near extreme masses. They're also universal, present wherever space-time curves, though usually too weak to notice. Earth's oceans feel tidal forces from the moon, water bulging toward and away from it. Your body experiences tiny tidal forces from Earth's gravity, unnoticeable but real. These forces are curvature made tangible, geometry affecting matter, space-time's shape translated into physical sensation. They remind us gravity isn't force but geometry, and geometry has gradients, variations, structure that pulls and pushes in subtle ways. Space-time intervals are invariant across reference frames. Though observers disagree about distances and durations, they agree on space-time intervals. This invariant quantity combines spatial and temporal separations into a single number that remains constant regardless of motion or perspective. It's the closest thing to absolute measurement in relativity. The interval between two events can be time-like, space-like, or null. Time-like intervals separate events that could be causally connected, where one could influence the other. Space-like intervals separate events that cannot influence each other. Null intervals separate events connected by light signals. All observers agree on which type an interval is, even though they measure different distances and times. This invariance is profound, revealing deep structure beneath relative measurements. Space and time trade off in precise ways, their combination remaining constant. The interval is real in a way individual measurements aren't, objective where coordinates are subjective. It's the geometry of space-time made manifest, the thing that actually matters beneath the shifting perspectives of different observers. De Sitter space describes exponentially expanding space-time. This solution to Einstein's equations describes a universe with positive cosmological constant, where space expands exponentially. De Sitter space is empty except for dark energy, which drives expansion at an accelerating rate. Our universe seems to be approaching De Sitter geometry as matter dilutes and dark energy dominates. In De Sitter space, distant objects accelerate away from each other, carried by expanding space itself. Eventually, expansion becomes so rapid that light from distant regions can never reach us, creating an event horizon beyond which we cannot see. The universe becomes lonely, each galaxy island isolated from all others. De Sitter space has unusual properties: no global time coordinate, no preferred reference frame, symmetry between space and time in certain ways. It's the geometry of eternal acceleration, of space winning its battle against matter, of expansion without end. As our universe ages, it becomes more De Sitter-like, approaching this strange geometry where space stretches forever, carrying everything apart into infinite separation. Anti-De Sitter space has negative curvature. Unlike De Sitter space, anti-De Sitter space has negative cosmological constant and contracts rather than expands. It's not physically realistic for our universe, but mathematically important, appearing in theoretical physics and quantum gravity research. Its geometry is hyperbolic, curving negatively like a saddle. Anti-De Sitter space has a boundary at infinity, where time flows normally, while interior time behaves strangely. This property makes it useful for studying holography, the principle that volume information can be encoded on boundaries. The ADS-CFT correspondence, a major theoretical breakthrough, relates gravity and anti-de Sitter space to quantum field theory on its boundary. This connection has revealed deep relationships between quantum mechanics and gravity, suggesting they're different descriptions of the same underlying reality. Though our universe is an anti-de Sitter, studying this geometry has illuminated fundamental physics, showing how space-time might emerge from quantum information, how gravity might be holographic, how seemingly different theories might be secretly identical. Geodesics are the straightest paths through curved space-time. In curved geometry, geodesics replace straight lines, representing the shortest or longest paths between points. Freely falling objects follow geodesics through space-time, moving along these natural paths determined by curvature. This is how gravity works in general relativity, not as force but as geometry guiding motion. A planet orbiting a star follows a geodesic, the straightest possible path through curved space-time. It's not being pulled but simply moving naturally through geometry. Light also follows geodesics, taking the shortest path through whatever curvature exists. When light bends near a star, it's following a geodesic through warped space-time, not being deflected by force. Geodesics are determined by the metric, the mathematical object describing space-time's shape. They represent natural motion, what objects do when nothing interferes. Every free particle follows a geodesic, written into space-time structure, guided by geometry rather than pushed by forces. It's elegant, simple, profound. Motion emerges from shape, dynamics from geometry. Everything following the contours of space-time itself. The metric tensor encodes all space-time geometry. This mathematical object contains complete information about space-time's shape, curvature and properties. The metric tells you distances, angles, volumes, how to calculate geodesics, everything about the geometry. Einstein's field equations determine the metric based on matter and energy distribution. The metric is a field, varying from point to point, describing local geometry everywhere. In flat space-time, it's simple and constant. Near massive objects, it becomes complicated, encoding curvature. The metric has 10 independent components in 4 dimensions, each one a function of position and time. Solving for the metric means solving Einstein's equations, finding the geometry that matches a given matter distribution. This is generally impossible analytically, requiring approximations or numerical methods. But the metric is the answer, the complete description of space-time. Know the metric and you know everything. How clocks tick, how rulers measure, how particles move, how light propagates. It's the fundamental object of general relativity, geometry itself made mathematical, space-time reduced to numbers that capture every curve and twist. If your mind is starting to wander, that's perfectly fine. These theories aren't meant to be memorized, only experienced, like watching clouds drift across the sky. Gravitational time, dilation, slows, clocks in strong fields. Time flows slower in stronger gravitational fields, an effect predicted by general relativity and confirmed by precise measurements. A clock on Earth's surface ticks slower than one in orbit, though the difference is tiny. Near a black hole, the effect becomes extreme, time nearly stopping at the event horizon. This isn't illusion or clock malfunction, but real time dilation, space-time geometry affecting temporal flow. Deeper in a gravitational well, space-time is more curved and time stretches. For someone falling toward a black hole, their own time seems normal, but to a distant observer they appear to slow down, freeze, redden, eventually fading from view. The falling person experiences finite proper time reaching the horizon, but infinite coordinate time passes outside. This asymmetry is real, measurable, fundamental. GPS satellites must account for gravitational time dilation, their clocks adjusted for weaker gravity at altitude. The effect reminds us time isn't absolute, isn't the same everywhere, but varies with position in spacetime's curved landscape. Frame, dragging occurs. Near, rotating masses. Rotating objects drag spacetime around with them, creating frame dragging or the lens-thirring effect. Near a spinning planet or star, space itself rotates, carrying everything with it. This effect is tiny for planets, but becomes significant near rotating black holes. Frame dragging means there's no truly stationary reference frame near a rotating mass. Even if you try to remain still, spacetime's rotation carries you along. Near a rotating black hole, frame dragging becomes so strong that nothing can remain stationary, everything forced to orbit in the rotation direction. This region is called the ergosphere. Frame dragging has been measured near Earth using satellites, confirming general relativity's predictions. The effect shows space-time isn't just curved but dynamic, responsive to motion as well as mass. Rotation twists space-time like stirring honey, creating vortices in the fabric of reality. It's another way geometry becomes active, another manifestation of spacetime's flexibility and responsiveness to matter and motion. The equivalence principle links gravity and acceleration. Einstein's key insight was that gravity and acceleration are equivalent, indistinguishable by local experiments. Someone in a closed elevator cannot tell whether they're stationary on Earth or accelerating through empty space at 1g. This equivalence principle became the foundation for general relativity. The principle has profound implications. It suggests gravity isn't a force but an effect of geometry, because acceleration affects geometry through relativity. It predicts gravitational time dilation, because accelerating clocks run slow. It predicts light bending in gravity, because light bends in accelerating frames. The equivalence isn't perfect at large scales where tidal forces reveal curvature, but locally it's exact. This principle guided Einstein to general relativity, suggesting that gravity must be geometric, that space-time must curve. It's beautiful in its simplicity, connecting seemingly different phenomena, showing that falling freely is natural motion, that gravity is acceleration through curved space-time. The principle remains central to modern physics, a touchstone for testing theories, a reminder that nature unifies what seems separate. Wormholes could connect distant regions of space-time. General relativity permits solutions containing wormholes, tunnels through space-time connecting distant locations. These Einstein-Rosen bridges could theoretically allow travel across vast distances without crossing the intervening space. However, they'd likely be unstable, collapsing before anything could traverse them. To keep a wormhole open requires exotic matter with negative energy density, something that might violate energy conditions. Whether such matter exists is unknown. Quantum effects might provide it, or perhaps not. Even if wormholes could exist, they'd probably be microscopic and short-lived. Traversable wormholes large enough for spacecraft remain purely speculative. They appear in the mathematics but might be forbidden by deeper principles we don't understand. Still, they're not obviously impossible, and that's remarkable. Spacetime's flexibility permits shortcuts, connections between distant points, topology more interesting than simple connectivity. Wormholes represent the strange possibilities lurking in general relativity's equations, reminders that spacetime might be more malleable than we imagine, that distance might be negotiable. Hawking radiation suggests black holes. Evaporate. Stephen Hawking discovered that quantum effects near event horizons cause black holes to emit radiation and slowly evaporate. This process is incredibly slow for large black holes, but suggests they're not eternal, that eventually they'll disappear in a final burst of energy. The radiation arises from quantum fluctuations near the horizon, where particle-antiparticle pairs spontaneously form. Normally they'd annihilate immediately, but at the horizon one can fall in while the other escapes, appearing as radiation. The black hole loses mass equal to the escaped particle's energy. Over immense timescales, this evaporation continues until the black hole vanishes. Hawking radiation connects quantum mechanics, general relativity and thermodynamics, showing black holes have temperature and entropy. It raises profound questions about information. What happens to information that fell into an evaporating black hole? The black hole information paradox remains unsolved, touching the deepest issues in theoretical physics. Hawking radiation shows space-time and quantum mechanics interact in unexpected ways. That even black holes aren't immune to quantum effects, that nothing in the universe is truly permanent. Space-time might be quantized at the Planck scale. Some theories propose space-time itself is quantized, coming in discrete units rather than being continuous. At the Planck length, about 10 to the minus 35 meters, space might be grainy, pixelated, made of minimal units that cannot be subdivided further. Loop quantum gravity, one approach to quantum gravity, predicts this quantization. Space would consist of tiny loops, time of discrete moments, both forming a foam-like structure at the smallest scales. This would mean space-time has a resolution limit, a finest possible detail beyond which the concepts of space and time break down. Quantized space-time would behave differently than continuous geometry, possibly resolving singularities, smoothing black hole centers and Big Bang into quantum structures. The idea remains speculative, untestable with current technology. But it suggests space-time might not be fundamental, might be built from something more basic, might be an emergent phenomenon like temperature or pressure. The implications are profound. Reality's stage might itself be quantized, made of discrete elements, space and time granular rather than smooth. Event horizons are one-way boundaries in space-time. An event horizon is a boundary beyond which events cannot affect outside observers. Black hole event horizons are the most famous examples, surfaces where escape velocity equals light speed. Nothing crossing inward can return or send signals out. From outside, event horizons appear frozen, time dilated to infinity. Infalling objects seem to slow down, redden, fade away, never quite crossing. But from the infalling perspective, the crossing happens in finite time, nothing special marking the moment. This asymmetry is real, built into space-time geometry. Event horizons are causal boundaries, dividing space-time into regions that cannot communicate. They're not physical surfaces but geometric features, places where light cones tip over, where all future directions point inward. Cosmological event horizons also exist, boundaries beyond which expanding space carries objects away faster than light can travel. These horizons are fundamental to space-time structure, showing how geometry can create absolute separations, unreachable regions, permanent isolation. They're beautiful and terrible, elegant mathematical features with profound physical consequences. The cosmological constant describes dark energy. Einstein introduced the cosmological constant to allow static universe solutions, then called it his greatest blunder when expansion was discovered. But observations now suggest it's real, representing dark energy that drives accelerating expansion. This constant appears in Einstein's equations as an intrinsic property of spacetime itself. Dark energy behaves like negative pressure, pushing space apart. It doesn't dilute as space expands, maintaining constant density, which seems strange but is mathematically consistent. The cosmological constant's value is tiny but non-zero, causing acceleration noticeable only at cosmic scales. Why it has this particular value is one of physics' deepest mysteries. Quantum field theory predicts a cosmological constant many orders of magnitude larger, a discrepancy called the cosmological constant problem. The actual value seems fine-tuned, just right to allow structure formation before acceleration dominates. This fine-tuning troubles physicists, suggesting missing understanding. The cosmological constant is spacetime's intrinsic energy, vacuum itself pushing outward, geometry active even in emptiness. Conformal geometry preserves angles but not distances. Conformal transformations change distances but preserve angles, a symmetry important in certain spacetime theories. Some physicists propose the universe's early moments had conformal symmetry, with no meaningful notion of scale or distance, only angular relationships. Roger Penrose's conformal cyclic cosmology suggests the universe's far future, when it's expanded to near emptiness, becomes conformally equivalent to another universe's beginning. The end of one cosmic cycle matches the start of the next, time becoming cyclic at the larger scales. This requires the universe to lose its sense of scale, all masses decaying, leaving only massless radiation. In such a state, distances become meaningless, only angles matter, and spacetime becomes conformally flat. The theory is speculative but mathematically elegant, suggesting time might be eternal, the universe cycling through infinite phases. Conformal geometry shows spacetime has hidden symmetries, ways of transforming that preserve some properties while changing others, mathematical flexibility that might reflect physical reality. Null surfaces are swept out by light rays. Light travels along null geodesics, paths with zero spacetime interval. Collections of these paths form null surfaces, two-dimensional surfaces in four-dimensional spacetime. Event horizons are null surfaces, as are light cones, important structures in causal analysis. Null surfaces are special because they're boundaries between time-like and space-like regions, between what can and cannot be causally connected. They represent the edges of causal influence, the limits of communication. Studying null surfaces helps understand black holes, gravitational waves, and causal structure generally. They're surfaces where time and space balance perfectly, where light can propagate but nothing else, where geometry becomes most constrained. Null surfaces are often singular, places where spacetime structure changes character, where different regions meet. They're mathematical objects with physical meaning, geometric features that organize spacetime's causal structure, showing how light defines what's possible, how photons trace reality's boundaries. If your eyes are growing heavy, don't fight it. Sleep is welcome here. The theories will continue whether you hear them or not. A quiet voice in the darkness. Penrose diagrams represent entire spacetimes compactly. These conformal diagrams compress infinite spacetime into finite pictures, showing causal structure clearly. Distances are distorted, but angles and causal relationships are preserved. Light rays always travel at 45-degree angles, making causal structure immediately visible. Penrose diagrams reveal spacetime's global structure, showing event horizons, singularities, infinity, all in one picture. They're invaluable for understanding black holes, cosmology, and causality. A Penrose diagram of a black hole shows the singularity as a space-like line at the top, the event horizon as a diagonal null surface, infinity as a boundary. You can see at a glance what regions can communicate, what's causally connected, what's forever separated. These diagrams are tools for thought, ways of visualizing four-dimensional geometry. They make the abstract concrete, the infinite finite, the complex simple. They're maps of space-time itself, compressed and clarified, showing reality's structure in elegant geometric form. Space-time singularities challenge physical theory. Singularities are points where curvature becomes infinite and general relativity breaks down. They appear in black hole centers and at the Big Bang, places where space-time itself seems to end or begin. Physics cannot describe singularities because all quantities become infinite, equations meaningless. Singularities might indicate where quantum gravity becomes essential, where general relativity's classical description fails. Perhaps quantum effects smooth singularities into finite structures, or perhaps they're real, genuine boundaries of space-time. The cosmic censorship hypothesis suggests singularities are always hidden inside event horizons, never naked and visible. This remains unproven, and counterexamples might exist. Singularities are troubling, places where our best theory admits defeat, where prediction becomes impossible. They're also fascinating hints that space-time isn't fundamental, that deeper structures await discovery. Singularities mark the edges of our understanding, points where reality becomes stranger than our mathematics can describe, where space and time themselves might dissolve into something we cannot yet imagine. Gravitational waves ripple through space-time. Accelerating masses create ripples in space-time geometry that propagate at light speed. These gravitational waves were predicted by Einstein and detected a century later by LIGO, confirming a major prediction of general relativity. The waves stretch and squeeze space itself as they pass. Gravitational waves carry energy away from their sources, causing orbiting objects to spiral together. They're produced by violent cosmic events, colliding black holes, merging neutron stars, supernovae. The waves detected so far came from events billions of light years away, their effects tiny but measurable. Detecting them required instruments sensitive to changes smaller than atomic nuclei across kilometers. Gravitational waves are space-time vibrating, geometry itself oscillating. They provide a new way to observe the universe, revealing events invisible to light. They confirm space-time is dynamic, responsive, capable of carrying waves like any other field. They show geometry as physical, real, something that can shake and ripple and carry information across cosmic distances. Kerr black holes rotate and drag space-time. Most black holes rotate, described by the Kerr solution to Einstein's equations. Rotating black holes are more complex than static ones, with two event horizons and an ergosphere where space-time is dragged around. They're probably more common than non-rotating black holes since most stars rotate. Inside the ergosphere, nothing can remain stationary. Everything must orbit in the rotation direction. The inner event horizon hides a ring singularity rather than a point. Kerr black holes might allow exotic possibilities, extracting energy from their rotation, or even travelling through the ring singularity to other universes, though this is purely speculative. The rotation adds structure, complexity, richness to black hole geometry. It shows how motion affects space-time, how angular momentum becomes geometric property. Kerr black holes are probably the reality of most astrophysical black holes, spinning remnants of collapsed stars carrying their parents' rotation into gravitational collapse, preserving angular momentum as geometry rather than motion. The Big Bang might be a space-time boundary. The universe's beginning appears as a singularity in general relativity, a point where space-time itself begins. Before the Big Bang, there might be no before, no time in which nothing existed. Time itself might begin with the universe, making questions about what came before meaningless. This idea troubles our intuition, which demands causes and predecessors. But if time begins at the Big Bang, causality begins there too. The universe doesn't need a cause because causation requires time, and time starts with the universe. This is consistent but philosophically challenging. Some theories avoid the initial singularity, suggesting the Big Bang was a bounce from a previous contracting phase, or an emergence from a quantum state, or a transition from another kind of geometry. The Big Bang remains mysterious, the ultimate boundary of space-time, the edge of our cosmic history. Whether it's truly a beginning or a transition from something else, we cannot yet say. Inflation theory proposes exponential early expansion. In the universe's first fraction of a second, space might have expanded exponentially, growing from subatomic to cosmic size almost instantaneously. This inflationary period would solve several cosmological puzzles: why the universe is so uniform, why it's so flat, why magnetic monopoles are absent. Inflation stretches quantum fluctuations to cosmic scales, creating the seeds for galaxy formation. It makes the observable universe a tiny patch of a much larger whole, most of which we cannot see. The mechanism driving inflation might be a scalar field, the inflaton, whose energy dominated early moments. When inflation ended, this energy converted to matter and radiation, reheating the universe. Inflation is widely accepted but not proven, its details uncertain. It suggests space-time can expand faster than light, not violating relativity because space itself expands, not objects moving through space. Inflation shows space-time's flexibility, its ability to stretch dramatically, its responsiveness to energy fields. It makes our observable universe a tiny bubble in something vastly larger. The multiverse might contain many spacetimes. Some theories suggest our universe is one of many, each with its own spacetime, physical laws and properties. These universes might be causally disconnected, unable to interact or communicate. The multiverse idea emerges from inflation, string theory, and quantum mechanics. Eternal inflation suggests new universes constantly bud off, each inflating separately, creating an infinite ensemble. String theory's landscape contains countless possible vacuum states, each potentially corresponding to a universe. Quantum mechanics' many worlds interpretation suggests reality branches continuously, creating parallel universes for each quantum outcome. These ideas are speculative, possibly untestable, but they arise naturally from well-established theories. If true, the multiverse means our space-time is just one among countless others, our physical laws arbitrary, our universe's properties not fundamental but accidental. This is philosophically radical, suggesting reality is far larger and stranger than we can observe. The multiverse remains controversial, some calling it science, others metaphysics, but it shows how seriously physicists take the possibility that space-time is not unique. Causal sets propose discrete space-time structure. This approach to quantum gravity suggests space-time is fundamentally a causal set, a discrete collection of events with causal relationships. Space and time emerge from the set structure, not existing fundamentally but arising from deeper order. In causal set theory, events are the basic elements, and causality determines which events can influence which others. Space-time geometry emerges statistically from the causal structure, like temperature emerging from molecular motion. The theory is background independent, not assuming pre-existing space-time. It suggests space-time is quantized, discrete at the Planck scale, with a fundamental graininess. Causal sets might explain the cosmological constant's value through quantum fluctuations in discrete geometry. The approach is mathematically elegant but incomplete, not yet making testable predictions. It represents a radical reimagining of space-time, suggesting the continuous geometry we experience is emergent, approximate, not fundamental. Reality at its deepest might be a network of causal relationships, with space and time as convenient fictions describing large-scale structure. Space-time might emerge from quantum entanglement. Recent research suggests space-time geometry might emerge from quantum entanglement patterns. Regions of space connected by smooth geometry correspond to highly entangled quantum states. This suggests space itself is a manifestation of quantum information. The ER-EPR conjecture proposes that Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen entanglement. Entangled particles might be connected by tiny wormholes, quantum entanglement and geometric connection being the same thing. If true, spacetime is woven from entanglement, quantum information creating geometry. This idea connects quantum mechanics and general relativity in unexpected ways, suggesting they're not separate theories but different aspects of something deeper. Space might not be fundamental but emergent, arising from quantum correlations. Distance might be a measure of entanglement, nearby points highly entangled, distant points less so. This is speculative but increasingly taken seriously, suggesting spacetime's deepest nature is quantum informational, geometry emerging from the patterns of quantum correlations that define reality. Asymptotically flat spacetime describes isolated systems. Spacetimes that become flat far from all masses are called asymptotically flat. They describe isolated objects like stars or black holes, surrounded by increasingly empty space. Far away, spacetime approaches Minkowski geometry, flat and simple. Asymptotic flatness is an idealization, since our universe contains matter everywhere and expands, but it's useful for studying isolated systems, understanding black holes, and defining conserved quantities like mass and angular momentum. At infinity, spacetime's curvature vanishes, and we can define total energy and momentum. These quantities are conserved, unchanging as the system evolves. Asymptotically flat spacetimes have well-defined notions of radiation escaping to infinity, like gravitational waves. They're the setting for most black hole physics, the context where singularity theorems apply. Though idealized, they capture essential features of real systems, allowing precise mathematical analysis. They show how spacetime can transition from curved to flat, from dynamic to static, from complex to simple, as distance increases. The Weyl curvature measures. Tidal distortion spacetime curvature divides into two parts: Ricci curvature, related to matter density, and Weyl curvature, representing tidal forces and gravitational waves. Weyl curvature describes how spacetime is stretched and squeezed, independent of local matter. In vacuum, only Weyl curvature exists, describing gravitational fields from distant sources. Gravitational waves are oscillations in Weyl curvature, ripples of tidal distortion propagating through space. Black holes have large Weyl curvature, creating strong tidal forces. Roger Penrose proposed the Weyl curvature hypothesis, that the universe began with zero Weyl curvature, highly special initial conditions. This might explain time's arrow, why the universe started ordered and evolved toward disorder. Weyl curvature grows as structure forms, black holes appear, and the universe becomes more complex. The hypothesis suggests spacetime's initial state was geometrically special, not just thermodynamically. It connects cosmology, gravity, and time's direction, suggesting deep relationships between geometry, entropy, and cosmic evolution. If some theories feel confusing, that's okay. They're meant to be felt more than understood, like music you don't need to analyze to enjoy. Alcubierre drive proposes space-time warping for travel. This theoretical concept suggests creating a bubble of warped space-time that moves faster than light, carrying a spacecraft inside. The bubble contracts space ahead and expands space behind, propelling the ship without locally exceeding light speed. It's permitted by general relativity's equations, but requires exotic matter. The energy requirements are enormous, possibly requiring more energy than exists in the observable universe. The exotic matter needed might not exist, or might violate energy conditions. Even if possible, the drive might be unstable or uncontrollable. Causality violations might occur, creating time travel paradoxes. The Alcubierre drive remains purely theoretical, a mathematical curiosity rather than an engineering proposal. But it shows spacetime's flexibility, how geometry might be manipulated if we understood it well enough. It suggests faster-than-light travel might not be forbidden by physics, only by engineering, that spacetime could theoretically be warped for transportation. The drive captures imagination, showing how general relativity permits strange possibilities, even if nature forbids them through practical constraints. Space-time has symmetries described by killing vectors. These mathematical objects represent space-time symmetries, directions along which geometry remains unchanged. A static space-time has a time-like killing vector, meaning geometry doesn't change over time. A spherically symmetric space-time has rotational killing vectors. Killing vectors correspond to conserved quantities. Time-like killing vectors give energy conservation. Space-like ones give momentum conservation. Black holes have killing vectors reflecting their symmetries, simplifying their mathematical description. Symmetries constrain possible geometries, making Einstein's equations easier to solve. Most realistic spacetimes have no symmetries, being irregular and complex. But symmetric solutions are important for understanding general principles, for building intuition about how spacetime behaves. They're the simple cases that illuminate the complex ones. Killing vectors show how symmetry and conservation connect, how geometry encodes physical principles, how spacetime shape determines what quantities remain constant. They're tools for analysis, mathematical structures that reveal spacetime's hidden regularities. The Ricci tensor relates curvature to matter. Einstein's field equations connect the Ricci tensor, describing certain aspects of curvature, to the stress-energy tensor, describing matter and energy. This relationship is the heart of general relativity, showing how matter curves space-time and curvature affects matter. The Ricci tensor captures how volumes change in curved space-time, how initially parallel geodesics converge or diverge. It's derived from the Riemann curvature tensor, which contains complete curvature information. Einstein's equations say the Ricci tensor equals the stress-energy tensor times a constant, directly linking geometry to matter. This equation is elegant, profound, revolutionary. It makes gravity geometric, shows space-time is dynamic, reveals matter and geometry as aspects of one thing. Solving Einstein's equations means finding the Ricci tensor that matches a given matter distribution, determining how space-time curves around stars, planets, black holes. The Ricci tensor is central to general relativity, the mathematical object that makes the theory work, that translates between matter and geometry. Cosmic strings might be defects in space-time. These hypothetical one-dimensional defects could have formed during the universe's early phase transitions, like cracks forming in freezing ice. Cosmic strings would be incredibly dense, stretching across cosmic distances, warping space-time around them. They might seed galaxy formation or produce gravitational waves. Cosmic strings are predicted by some grand unified theories but haven't been observed. If they exist, they'd be thinner than atoms but immensely massive, containing energy densities from the early universe. Space-time around a cosmic string has a deficit angle, a missing wedge of space, creating unusual lensing effects. Strings might form loops that oscillate and decay, radiating gravitational waves. They're speculative but not impossible, representing another way space-time could have structure, defects in reality's fabric. Cosmic strings show how topology can affect space-time, how the universe's history might leave geometric scars, how phase transitions in the early universe might create lasting structures. They're fossils of cosmic evolution, if they exist. Defects that remember when the universe was young. The Einstein-Cartan theory includes torsion. General relativity describes curved space-time without torsion, but Einstein-Cartan theory adds torsion, a twisting of space-time related to spin. In this extension, not just mass but also spin affects geometry, creating torsion in addition to curvature. Torsion would be significant only at extremely high densities, perhaps inside black holes or at the Big Bang. It might prevent singularities, replacing them with bounces or transitions. Spin would couple to torsion the way mass couples to curvature. Einstein-Cartan theory is a natural extension of general relativity, mathematically consistent, but its effects are probably too small to detect. It shows space-time might have richer structure than general relativity describes, additional geometric properties beyond curvature. Torsion represents another way space-time can be distorted, another response to matter, another geometric degree of freedom. The theory remains speculative, but reminds us that spacetime's properties might not be fully captured by Einstein's original equations. Mach's principle suggests inertia comes from distant matter. Ernst Mach proposed that inertia, resistance to acceleration, arises from interaction with all other matter in the universe. In empty space with no other matter, objects would have no inertia. This idea influenced Einstein but isn't fully incorporated into general relativity. Mach's principle suggests spacetime is an absolute but relational, defined by matter distribution. Rotation would be meaningful only relative to distant stars, not to absolute space. General relativity partially implements this. Matter determines geometry, and geometry affects motion. But spacetime can exist without matter in general relativity, contrary to Mach's principle. Some solutions, like Gödel's rotating universe, violate Machian ideas. The principle remains philosophically appealing but not rigorously defined or proven. It suggests spacetime might be emergent from matter relations, not existing independently. It questions whether spacetime is fundamental or derived, whether geometry is primary or secondary. Mach's principle shows how deeply our understanding of spacetime connects to philosophy, how questions about reference frames and absolute versus relative motion remain subtle. The Schwarzschild solution describes non-rotating black holes. This exact solution to Einstein's equations describes spacetime around a spherically symmetric, non-rotating mass. It was the first exact solution found, discovered by Karl Schwarzschild months after general relativity was published. The solution describes black holes, though that wasn't recognized immediately. The Schwarzschild metric contains an event horizon at the Schwarzschild radius, where escape velocity equals light speed. Inside this radius, all paths lead to the central singularity, time and space exchanging roles in a sense. The solution is static, unchanging in time, and spherically symmetric, the same in all directions. It's the simplest black hole geometry, the baseline for understanding more complex cases. Real black holes probably rotate, described by the Kerr solution, but Schwarzschild provides essential intuition. The solution shows how mass warps space-time, creating regions from which nothing escapes, how geometry can trap even light. It's beautiful mathematics with profound physical meaning, the first glimpse of black holes hidden in Einstein's equations. Naked singularities might exist without event horizons. The cosmic censorship hypothesis suggests singularities are always hidden inside event horizons, never visible to distant observers. But some solutions to Einstein's equations contain naked singularities, visible from outside. Whether these occur in nature is unknown. Naked singularities would be problematic, allowing unpredictable influences from regions where physics breaks down. They might violate causality, create paradoxes, make prediction impossible. Most physicists believe cosmic censorship holds, that nature prevents naked singularities through some mechanism, but proving this is difficult, and counter-examples might exist. Naked singularities represent the possibility that spacetime's pathologies could be visible, that singularities might not always hide behind horizons. They're disturbing theoretically, suggesting spacetime could have unprotected breaks, places where physics fails openly. Whether cosmic censorship is a law or wishful thinking remains uncertain, one of general relativity's deepest open questions. Spacetime diagrams visualize events and world lines. These graphs plot time vertically and space horizontally, showing how objects move through spacetime. Each point represents an event, a specific place and time. An object's path through spacetime is its world line, a curve on the diagram. Spacetime diagrams make relativity intuitive, showing how different observers perceive events differently, how simultaneity is relative, how time dilation and length contraction work. Light rays appear as diagonal lines at 45 degrees. Objects moving slower than light have world lines steeper than 45 degrees. The diagrams reveal causal structure, showing which events can influence which others. They're pedagogical tools, ways of visualizing four-dimensional geometry in 2 dimensions. Space-time diagrams transform abstract concepts into concrete pictures, making relativity's strangeness comprehensible. They show how space and time mix under motion, how perspectives differ, how causality constrains what's possible. These diagrams are maps of reality's structure, simple drawings that capture profound truths about space-time's nature. The Unruh effect predicts accelerating observers. See radiation. An accelerating observer in empty space would detect thermal radiation, while an inertial observer sees only vacuum. This Unruh effect connects acceleration, temperature, and quantum fields in surprising ways. It's analogous to Hawking radiation, but for acceleration rather than gravity. The effect is tiny for normal accelerations, requiring enormous acceleration to produce detectable temperature. It shows vacuum isn't absolute but observer-dependent, that what counts as empty space depends on motion. The Unruh effect hasn't been directly observed but is theoretically solid, following from quantum field theory in curved space-time. It suggests deep connections between gravity, acceleration, and thermodynamics, that horizons create temperature, that geometry affects quantum fields. The effect is another manifestation of relativity's strangeness, showing how different observers experience different realities, how acceleration creates phenomena that don't exist for inertial observers. It hints that space-time and quantum fields are intimately connected, that geometry and quantum mechanics cannot be fully separated. There's no test at the end, no need to prove you are listening. Your mind can wander where it wants, to memories, to dreams, to nothing at all. The brain world scenario suggests hidden dimensions. In this picture, our four-dimensional space-time is a brain, a membrane embedded in higher dimensional space. We're confined to the brain, unable to perceive the extra dimensions directly. Gravity might propagate through all dimensions, explaining why it's weaker than other forces. The brain world suggests our universe is a surface in a larger reality, like a sheet of paper in 3-dimensional space. Other brains might exist parallel to ours, entire universes separated by tiny distances in extra dimensions, but unreachable, because we cannot move perpendicular to our brain. This scenario emerges from string theory, which requires extra dimensions. The brain world could explain various puzzles, from gravity's weakness to dark matter. It's speculative but mathematically consistent, representing another way reality could be stranger than it seems. The idea shows how space-time might not be all there is, how additional dimensions could exist undetected, how our universe could be just one layer in a larger structure. Traversable wormholes require exotic matter. To keep a wormhole open long enough to travel through requires matter with negative energy density, violating the null energy condition. Such exotic matter might not exist, or might be forbidden by quantum constraints. Even if it exists, stabilizing a wormhole might be impossible. Traversable wormholes appear in science fiction but remain theoretical speculation. The mathematics permits them, but physics might forbid them. Quantum effects could provide negative energy locally, but sustaining it in the quantities needed seems impossible. Even if traversable wormholes could exist, they'd probably be microscopic and unstable. Creating one might require manipulating space-time with technologies far beyond anything conceivable. Wormholes represent the boundary between what's mathematically possible and physically real, showing how general relativity's flexibility might exceed nature's willingness. They're dreams encoded in equations, possibilities that probably remain forever impossible, reminders that mathematics can describe things that don't exist. The Gödel universe contains closed, time-like curves everywhere. Kurt Gödel discovered a solution to Einstein's equations describing a rotating universe where time travel is possible everywhere. Closed time-like curves pervade this space-time, allowing travel to one's own past. The solution is exact, mathematically valid, but probably not physically realistic. Gödel's universe doesn't expand, violating observations. It rotates relative to distant matter, violating Mach's principle. But it shows general relativity permits time travel, that the equations don't forbid closed time-like curves. Whether nature allows them is another question. Gödel's solution troubled Einstein, suggesting his theory might permit causality violations. It remains a curiosity, a mathematical possibility that probably doesn't describe reality, but it shows space-time's flexibility, how strange geometries can satisfy Einstein's equations, how time might be less linear than we assume. Gödel's universe is a thought experiment in mathematical form, exploring what's possible within general relativity's framework, revealing unexpected features of space-time geometry. Causal horizons limit. Observable universe. As space expands, distant objects recede faster than light, creating a cosmological horizon beyond which we cannot see. Light from beyond this horizon hasn't had time to reach us and never will. This horizon is a causal boundary, permanently separating regions of space-time. Our observable universe is finite, bounded by this horizon, even though the full universe might be infinite. The horizon grows as time passes, revealing new regions, but it always exists, always limiting what we can observe. Objects crossing the horizon disappear from view forever, carried away by expansion. This creates a kind of loneliness. Most of the universe is forever beyond our reach, unknowable, existing but inaccessible. Causal horizons show how expansion affects causality, how spacetime's dynamics create absolute separations, their geometric features with profound implications, boundaries that divide reality into regions that cannot interact, that define what's knowable and what must remain mystery. The Raychaudhuri equation describes geodesic focusing. This fundamental equation governs how bundles of geodesics converge or diverge, essential for understanding singularity formation. It shows that under reasonable energy conditions, geodesics tend to focus, converging toward singularities. This focusing is key to singularity theorems. The Raychaudhuri equation doesn't depend on Einstein's field equations, holding in any space-time. It's purely geometric, describing how test particles moving on geodesics behave collectively. The equation predicts that expansion eventually stops and reverses, that geodesic bundles develop caustics, that focusing is generic. Combined with energy conditions, it implies singularities are almost inevitable, that spacetime cannot be geodesically complete under normal circumstances. The equation is elegant, simple, powerful, revealing deep truths about spacetime geometry. It shows how curvature affects geodesic bundles, how matter's presence makes focusing inevitable, how singularities emerge naturally from reasonable assumptions. Asymptotic safety suggests gravity becomes scale invariant. At extremely high energies, quantum gravity might reach a fixed point where it becomes scale invariant with no characteristic length. This asymptotic safety would make quantum gravity well-defined and predictable, avoiding the infinities that plague other approaches. If gravity is asymptotically safe, it would be a complete theory at all scales, requiring no additional structure. Spacetime would remain meaningful even at the Planck scale, not dissolving into something else. This contrasts with approaches suggesting spacetime is emergent or quantized. Asymptotic safety is an active research program, not yet proven but promising. It would mean gravity is simpler than expected, that general relativity extends to quantum scales with appropriate modifications. The idea shows how quantum field theory techniques might apply to gravity, how spacetime might remain continuous even in quantum regimes, how the theory might be self-consistent without requiring strings or loops. The Shapiro time delay shows light slows in gravity. Light passing near a massive object takes longer to travel than it would in flat space, not because it slows down, but because spacetime is curved, lengthening the path. This Shapiro delay has been measured precisely, confirming general relativity's predictions. Radar signals bounced off planets take longer when passing near the Sun, arriving slightly delayed. This delay is gravitational time dilation affecting the light's journey, showing how gravity affects time as well as space. The effect is small but measurable, another confirmation of general relativity's accuracy. It shows light follows geodesics through curved space-time, taking longer when curvature is present. The Shapiro delay is used to test general relativity, to measure masses of distant objects, to probe space-time geometry. It's a subtle effect, easily overlooked, but it reveals spacetime's curvature directly, showing how gravity affects light's travel time. Gravitational lensing bends light around massive objects. Mass curves spacetime, and light follows this curvature, creating gravitational lensing. Distant galaxies appear distorted, magnified or multiplied when viewed past massive foreground objects. This effect confirms general relativity and serves as a tool for astronomy. Einstein predicted gravitational lensing, and it was first observed during a solar eclipse in 1919, making him famous. Today, lensing reveals dark matter distribution, magnifies distant galaxies, and creates spectacular cosmic mirages. Strong lensing produces multiple images or Einstein rings. Weak lensing subtly distorts galaxy shapes, revealing invisible mass. Microlensing brightens stars temporarily when compact objects pass in front. Gravitational lensing shows spacetime's curvature directly, makes the invisible visible, turns gravity into a telescope. It's beautiful and useful, revealing the universe's structure, confirming relativity's predictions, showing how light traces spacetime's shape. The cosmological principle assumes large-scale uniformity. This principle states the universe is homogeneous and isotropic on large scales, the same everywhere and in all directions. It's an assumption, not a proven fact, but observations support it. The cosmological principle simplifies cosmology, allowing standard models to be constructed. If true, there's no special place in the universe, no center, no edge, no preferred direction. The principle reflects Copernican thinking. We're not special, our location is typical. It implies the universe's large-scale geometry is simple, describable by a few parameters. Observations of the cosmic microwave background confirm remarkable uniformity, supporting the principle. But the principle is approximate, holding only at the largest scales. Locally, the universe is lumpy, full of structure, galaxies, and voids. The cosmological principle is a working assumption, useful and approximately true, guiding how we model spacetime at cosmic scales. If you've drifted in and out, that's perfect. These theories are companions, keeping you company as you drift, asking nothing, demanding nothing, just offering gentle wonder. Curvature, singularities, differ from coordinate singularities. Some singularities are real, where curvature becomes infinite, while others are artifacts of coordinate choices. Coordinate singularities disappear when different coordinates are used, revealing the spacetime is actually smooth. Distinguishing these is crucial for understanding spacetime structure. The Schwarzschild solution appears singular at the event horizon in standard coordinates, but this is a coordinate singularity. In different coordinates, the horizon is smooth and the singularity vanishes. The central singularity, however, is real, a curvature singularity where spacetime truly breaks down. Coordinate singularities are mathematical artifacts, not physical. They arise from poor coordinate choices, like the singularity at Earth's poles in latitude-longitude coordinates. Recognizing coordinate singularities prevents misunderstanding spacetime geometry, helps identify what's physically meaningful. Real singularities are invariant, appearing in all coordinate systems, marking genuine pathologies in space-time structure. The Friedmann equations govern cosmic expansion. These equations, derived from general relativity, describe how the universe's scale factor changes over time. They relate expansion rate to matter density, curvature, and cosmological constant. The Friedmann equations are the foundation of modern cosmology, describing the universe's evolution. The equations predict the universe either expands forever, recollapses, or expands at decreasing rate approaching zero. Which scenario occurs depends on total energy density. Observations suggest our universe will expand forever, accelerating due to dark energy. The Friedmann equations are remarkably simple, reducing the universe's complexity to a few parameters. They assume the cosmological principle, treating the universe as homogeneous and isotropic. Despite this simplification, they describe cosmic evolution accurately, matching observations from the Big Bang to present. The equations show how space-time dynamics depend on contents, how matter and energy determine cosmic fate. The Tolman-Oppenheimer-Volkoff equation describes stellar equilibrium. This equation determines the internal structure of static, spherically symmetric stars in general relativity. It balances gravitational collapse against pressure, showing how massive stars can exist without collapsing. The equation predicts a maximum mass for neutron stars, beyond which collapse to black holes is inevitable. The TOV equation extends Newtonian hydrostatic equilibrium to relativistic gravity, accounting for pressure's contribution to gravity and space-time curvature. It shows that pressure doesn't just resist collapse but also contributes to gravity, creating a feedback that limits stellar masses. The equation predicts neutron stars cannot exceed about 3 solar masses, a limit confirmed by observations. Above this mass, no known pressure can resist collapse, and black holes form. The TOV equation is essential for understanding compact objects, stellar remnants, and the boundary between stars and black holes. It shows how general relativity constrains stellar structure, how space-time curvature affects equilibrium. The Vidya metric describes radiating black holes. This solution to Einstein's equations describes a black hole emitting or absorbing radiation, with mass changing over time. Unlike the static Schwarzschild solution, Vidya spacetime is dynamic, with energy flowing across the event horizon. It models black holes more realistically than static solutions. The Vidya metric is used to study black hole formation, evaporation, and interaction with surroundings. It describes how event horizons change as mass changes, how radiation affects space-time geometry. The solution is relatively simple, making it useful for theoretical studies. It shows black holes aren't necessarily static but can evolve, gaining or losing mass, changing size. The Vidya metric bridges static and fully dynamic solutions, providing insight into time-dependent processes. It's a tool for understanding how black holes interact with their environments, how they form from collapsing matter, how they might evaporate through Hawking radiation. Proper distance measures space between simultaneous events. In cosmology, proper distance is the distance between objects at a given cosmic time, accounting for expansion. It's the distance you'd measure if you could freeze expansion and lay rulers end to end. Proper distance changes as the universe expands, growing even though objects don't move through space. This concept is crucial for understanding cosmology, where space itself expands. Objects can be farther apart than light could have travelled since the Big Bang because space between them has expanded. Proper distance distinguishes expansion from motion, showing how space-time dynamics differ from particle motion. It's the distance that matters for determining how much space exists between objects at a given time. Proper distance grows with scale factor, directly reflecting expansion. Understanding it clarifies how cosmic expansion works, how distances change without objects moving, how space-time itself evolves. The Petrov classification categorizes space-time curvature. This scheme classifies spacetimes based on their Weyl curvature tensor's algebraic properties. The classification has 5 types, from algebraically special to algebraically general. Many important solutions, including black holes and gravitational waves, are algebraically special. The Petrov classification reveals geometric structure, showing which spacetimes have special symmetries or properties. Type D includes Schwarzschild and Kerr black holes, showing their curvature has particular algebraic form. Type N describes gravitational waves, showing their curvature structure. The classification helps solve Einstein's equations, identify symmetries, and understand spacetime geometry. It's a mathematical tool, organizing solutions by their geometric properties. The classification shows spacetime curvature has structure beyond mere numbers, that different geometries have different algebraic characters, that curvature can be categorized in meaningful ways. The Israel junction conditions match spacetimes across boundaries. When two spacetime regions meet at a boundary, Israel junction conditions ensure the geometry matches smoothly. These conditions are essential for modeling shells, membranes, and boundaries in general relativity. They determine how curvature and matter distribute across interfaces. Junction conditions allow constructing spacetimes from pieces, matching interiors to exteriors, modeling thin shells and surfaces. They're used to study stellar surfaces, bubble nucleation, and branes. The conditions ensure energy and momentum are conserved across boundaries, that geometry is continuous or has well-defined discontinuities. They generalize boundary conditions from other physics, applying them to spacetime geometry. Junction conditions show how different spacetime regions can be joined, how interfaces behave, how boundaries affect geometry. They're mathematical tools for building complex spacetimes from simpler pieces, ensuring consistency and conservation. The Bondi mass describes energy in asymptotically flat spacetimes. In spacetimes that become flat at infinity, the Bondi mass measures total energy including gravitational radiation. Unlike ADM mass, which is defined at spatial infinity, Bondi mass is defined at null infinity, along light rays escaping to infinity. Bondi mass decreases as gravitational waves carry energy away, showing energy lost through radiation. It's a function of time at null infinity, changing as waves propagate outward. The Bondi mass concept is crucial for understanding gravitational wave emission, energy conservation, and radiation reaction. It shows spacetime can lose energy through geometry itself radiating, that gravitational waves carry real energy away from systems. Bondi mass is a global property, defined at infinity, reflecting the entire spacetime's energy content. It's a sophisticated concept, requiring careful treatment of infinity, but essential for understanding radiation in general relativity. The Birkhoff theorem states spherical vacuum is static. This theorem proves that any spherically symmetric vacuum solution to Einstein's equations must be static, described by the Schwarzschild metric. There are no spherically symmetric gravitational waves, no time-dependent spherical vacuum solutions. The theorem constrains possible spacetime geometries. Birkhoff's theorem means a pulsating spherical star doesn't emit gravitational waves, because the exterior remains static. Only non-spherical dynamics produce radiation. The theorem simplifies many problems, showing Schwarzschild is the unique spherical vacuum solution. It's a powerful constraint, limiting what geometries are possible, showing how symmetry restricts dynamics. The theorem reveals deep connections between symmetry and time independence, showing spherical symmetry is especially restrictive. It's one of general relativity's elegant mathematical results, a theorem that clarifies spacetime structure. We're near the end now. Let the final theories wash over you like gentle waves, carrying you deeper into rest, into calm, into the soft embrace of sleep. The Penrose singularity theorem predicts inevitable collapse. Roger Penrose proved that under reasonable conditions, gravitational collapse must produce singularities. If a trapped surface forms where all light rays converge inward, a singularity is inevitable. This theorem shows singularities aren't artifacts of symmetry, but generic features of collapse. The theorem assumes energy conditions and causal structure, not symmetry. It proves singularities occur in realistic gravitational collapse, that black holes generically have singular centers. Combined with Hawking's work on cosmology, singularity theorem suggests the Big Bang was also singular. The theorems are mathematical, proving inevitability under assumptions, not describing what singularities are. They show general relativity predicts its own breakdown, that the theory contains its own limits. Penrose's theorem is fundamental, revealing deep truths about space-time, showing collapse leads to singularities almost inevitably. The Hawking singularity theorem implies a Big Bang singularity. Stephen Hawking proved that if the universe expands and contains normal matter, running time backward implies a singularity in the past. This theorem suggests the Big Bang was singular, that space-time itself began at a definite point. Combined with Penrose's work, it shows singularities are generic in general relativity. The theorem assumes energy conditions and cosmic expansion, proving the universe cannot be eternal into the past. It suggests time itself began, that there's no before the Big Bang. The theorem is classical, not accounting for quantum effects which might avoid the singularity. But classically, the theorem is rigorous, showing general relativity predicts its own beginning. Hawking's theorem is profound, suggesting space-time is not eternal, that the universe has a finite age, that time itself began with the Big Bang. The positive energy theorem guarantees mass is non-negative. This theorem proves that in asymptotically flat spacetimes, satisfying energy conditions, total mass cannot be negative. Zero mass occurs only for flat spacetime. The theorem ensures spacetime is stable, that negative mass configurations don't exist, that energy is well defined. The positive energy theorem was a major achievement, proving a long-suspected result. It shows general relativity is consistent, that total energy is always positive, that space-time doesn't have pathological negative energy states. The proof is sophisticated, using spinors and advanced mathematics. The theorem constrains possible spacetimes, ensures stability, and validates energy definitions. It's a deep result showing general relativity's mathematical structure is sound, that the theory has built-in protections against unphysical configurations. The cosmic no-hair theorem suggests universes become smooth. This theorem states that expanding universes with positive cosmological constant eventually become indistinguishable from de Sitter space, losing all structure and irregularities. Cosmic no-hair means initial conditions are forgotten, that universes smooth out over time, that expansion erases complexity. The theorem applies to universes dominated by dark energy, like ours in the far future. Eventually all matter dilutes, all structure disappears, and only smooth exponential expansion remains. The universe becomes featureless, homogeneous, isotropic, approaching de Sitter geometry. This is the ultimate fate of our universe if dark energy persists. Eternal expansion, infinite loneliness, all complexity erased. The cosmic no-hair theorem shows how dynamics erase initial conditions, how expansion smooths irregularities, how the universe's end state is simple regardless of its beginning. The membrane paradigm treats horizons as physical surfaces. This approach treats black hole event horizons as if they were physical membranes with properties like viscosity, electrical resistance, and temperature. Though horizons aren't material surfaces, the membrane paradigm provides intuitive understanding and simplifies calculations. The paradigm assigns properties to horizons based on how they interact with external fields. It makes black hole physics more concrete, translating geometric properties into familiar physical concepts. The membrane has entropy, temperature, and other thermodynamic properties, making black hole thermodynamics intuitive. The approach is a calculational tool, not claiming horizons are literally membranes, but treating them as if they were. It shows how geometry can mimic material properties, how space-time features can be understood through physical analogies. The membrane paradigm bridges geometry and physics, making abstract concepts tangible. The immensity parameter appears in loop quantum gravity. This dimensionless constant appears in loop quantum gravity's formulation, affecting the relationship between area and entropy. Its value determines black hole entropy in the theory, connecting quantum geometry to thermodynamics. The immensity parameter is mysterious, its value not predicted but chosen to match Bekenstein-Hawking entropy. The parameter reflects ambiguities in quantizing gravity. Different choices lead into different quantum theories. Its physical meaning is unclear, and determining its value from first principles remains an open problem. The immensity parameter shows loop quantum gravity isn't unique, that quantization choices affect predictions, that the theory has free parameters. It's a technical detail with deep implications, showing quantum gravity's formulation involves choices whose physical meaning we don't fully understand. The parameter connects quantum geometry to thermodynamics, showing how area quantization relates to entropy. The Gibbons-Hawking-York boundary term completes the action. In general relativity's action formulation, a boundary term is needed for well-defined variational principle. This term, proposed by Gibbons, Hawking, and York, ensures the action principle works correctly when spacetime has boundaries. It's essential for path integral approaches to quantum gravity. The boundary term contributes to conserved quantities and thermodynamics, affecting energy definitions and partition functions. It shows action principles in gravity are subtle, requiring careful boundary treatment. The term is proportional to boundary curvature, ensuring the action is finite and well-defined. It's a technical necessity that has deep physical consequences, affecting how we formulate quantum gravity, calculate thermodynamic properties, and define energy. The Gibbons-Hawking-York term shows gravity's action principle is richer than other theories, requiring additional structure at boundaries. The Cartan formalism uses connection and curvature forms. This approach to general relativity uses differential forms and connection one forms, providing elegant mathematical formulation. The Cartan formalism emphasizes geometry, treating curvature and torsion as fundamental objects. It's particularly useful for understanding gauge theory aspects of gravity. Cartan's approach makes calculations more efficient, reveals symmetries clearly, and connects gravity to other gauge theories. It treats space-time as a fiber bundle, with connection defining parallel transport. Curvature measures how parallel transport around loops fails to return to the starting point. The formalism is mathematically sophisticated but geometrically intuitive, showing gravity's structure clearly. It's an alternative to metric-based approaches, emphasizing different aspects of geometry. The Cartan formalism shows general relativity can be formulated in multiple ways, each revealing different features, each useful for different purposes. The Wheeler-DeWitt equation describes quantum cosmology. This equation is the Schrödinger equation for the universe's wave function, attempting to quantize cosmology. It's timeless, containing no time variable, describing the universe's quantum state without reference to external time. The Wheeler-DeWitt equation is controversial, its interpretation unclear. The equation treats spacetime geometry as quantum, with wave functions over possible geometries. It's difficult to solve and interpret, raising questions about time's nature, about what the wave function means, about how to extract predictions. The Wheeler-DeWitt equation represents an attempt to quantize general relativity directly, treating space-time itself as quantum. It's a starting point for quantum cosmology, though its physical meaning remains debated. The equation shows how profoundly quantum mechanics and general relativity clash, how combining them raises deep conceptual issues about time, causality, and reality's nature. The Kodama state is a candidate vacuum for quantum gravity. In certain approaches to quantum gravity, the Kodama state is proposed as the vacuum state, the lowest energy configuration of quantum space-time. It's constructed using de Sitter geometry, potentially relevant for our universe's dark energy-dominated future. The state's physical interpretation is debated. The Kodama state might describe the universe's quantum ground state when dark energy dominates, providing a starting point for quantum cosmology. It's related to Chern-Simon's theory, showing deep connections between gravity and gauge theories. The state is controversial, its properties not fully understood, its role in quantum gravity unclear. It represents an attempt to define what quantum spacetime's vacuum is, what the lowest energy state of geometry itself might be. The Kodama state shows quantum gravity involves choosing vacuum states, defining what counts as empty space, questions without obvious answers. And so our quiet journey through space-time comes to a gentle close. We've travelled far tonight, from the fabric of reality to the quantum foam beneath, from black holes to the Big Bang, touching on questions that span the breadth of human understanding. The theories behind us now, like stars fading into dawn. Some theories offered answers, others only deeper questions. Some felt solid, others shimmered like mirages. But all of them carried a piece of humanity's endless curiosity, our refusal to accept the world at face value, our need to wonder. These theories, some ancient and some born yesterday, represent our attempts to understand the fundamental nature of space and time, the stage upon which everything unfolds, the fabric from which reality is woven. Theories are strange things. They're not quite facts, not quite fantasies. They live in the space between what we know and what we imagine. They're humanity's way of reaching toward truth with imperfect hands, building bridges across chasms of ignorance. Some will be proven right, others will fade, but the reaching itself, the wondering, never stops. If your eyes are already heavy, that's just fine, perfect even. Let the last traces of curved space-time fade behind your thoughts, becoming less distinct, less important. Let your breath carry you softly into rest, each exhale releasing a little more tension, each inhale drawing you deeper into calm. There's still so much more to discover, endless theories waiting, but for now you've learned enough. You've wondered enough. You've travelled far through mysteries and questions, and space-time can wait until morning, patient and unchanging, ready whenever you return. You don't need to remember any of this, not the names, not the details, not even the theories themselves. They were never meant to be memorized, only experienced, like watching clouds drift across the sky. What matters is not what you retain, but how you felt while listening. The gentle stimulation of curiosity, the soft pleasure of learning, the quiet comfort of questions asked in darkness. That's enough. That's everything. Notice how your body has grown heavier as we've talked, how your muscles have softened, how even the weight of your thoughts has decreased. This is the natural rhythm of rest, the way consciousness gradually releases its grip, letting you drift. You don't need to force it. You don't need to try. Just allow it, the way you'd allow yourself to float in calm water, trusting the water to hold you, trusting the darkness to be safe. There's nothing you need to do now. No answers to chase, no puzzles to solve, no theories to understand. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep. So let go. Let your mind wander where it will, through dreams or darkness, through memories or nothing at all. Thank you for spending this time with me. for letting me guide you through these theories, these questions, these mysteries. Thank you for your curiosity, for your willingness to wonder, for choosing to end your day with learning rather than emptiness. It means something, this choice you've made. It says something about who you are, someone who seeks understanding even in the quiet moments before sleep. And I'm grateful to be part of your evening, part of your routine, part of the quiet ritual that carries you from waking into sleep. You're not alone in this. Right now, all across the world, others are listening too, drifting through these same theories, wondering these same questions. Some are ahead of you, already deep in dreams. Others are just beginning. But you're all connected by this shared experience, this common journey through mystery and wonder, a quiet community of curious minds, seeking rest and knowledge in the same breath, finding peace in questions that have no answers. Tomorrow night, we'll explore another topic, another journey through wonder. But that's tomorrow. Tonight is for rest, for dreams, for letting go of everything except the gentle pull of sleep. Imagine yourself now, floating through the theories we've explored, passing by them as if through constellations in the night. Questions above, questions below, a galaxy of wonder all around you, and you at the quiet center resting in the knowledge that mystery is not something to fear, but something to embrace, that not knowing is not failure, but invitation, that the universe keeps secrets not to frustrate us, but to keep us curious, to keep us reaching, to keep us human. Let that thought comfort you. Let it wrap around you like a blanket woven from starlight and uncertainty, soft and strange and somehow perfect. The theories we've explored tonight are just whispers in an infinite conversation, questions asked across time, mysteries that connect us all. There's nothing left to do now, no answers to chase, no puzzles to solve, no theories to understand. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep, so let go. Let your mind wander where it will, through dreams or darkness, through memories or nothing at all. Let your consciousness dim like a sunset, gradually, naturally, beautifully. And know that when you wake, the theories will still be here, the questions will still wait, and the universe will still be strange and wonderful. I hope you sleep well and dream softly. May your rest be deep, your dreams be gentle, and your tomorrow be bright. Thank you for being here. Good night.